Yes, we're listening.
Okay, great. Yeah, I'll just go ahead and let me know if you find any issues on your side. Yeah, thank you again for the introduction, and also thanks for inviting me to this workshop. It's really my pleasure to present today. And today I'm going to basically present some of the recent works we have done on scaling up 3D large models, especially on scaling up 3D large reconstruction models and rendering models. So first, I just like to add a little more background about myself. So I recently joined a startup company called Hubot as the VP of Research and Development. And we are still a small AI and robotics startup with a mission to build intelligent general purpose robots. And we work on various critical problems on robotics, including building a large AI foundation models with strong spatial and temporal understanding. And prior to joining Hubot, I was a research scientist at Adobe Research till actually last December. And at Adobe, I was working on problems like Neural 3D, 3D large models, and Gen AI foundation models. So in this talk, the works I'm presenting today are actually mostly done when I was working at Adobe with my former colleagues, interns, and collaborators. And in general, the key problem I studied at Adobe was the classical computer vision problem of multi-view 3D reconstruction and rendering. And this is, of course, a long-standing task, and the community has come up with various solutions on many different problems and domains. For example, like researchers have in fact built a complete photogrammetry pipeline with traditional methods like structure from motion, multi-view stereo, and 3D fusion, and others. And also recent years, we have also seen the significant advancements in neural rendering with methods like NeRF and 3D Gaussian splatting. And these methods typically consider input images with known camera poses and achieve neural scene reconstruction via a processing optimization process supervised by rendering losses. And on the other hand, the community has also developed various learning-based feed-forward models that can generalize across scenes, including the CNN-based deep multi-view stereo methods, and also the recent transformer-based models like our large reconstruction models and Duster. And while these methods have made significant progress, I feel one critical problem that still remain in the community is about how could we build a 3D model that can truly scale. In some sense, this is different from other communities, like language processing has already had their autoregressive large transformers, and image generation also now has the diffusion transformers, and those models can actually scale really well on their tasks. But for 3D reconstruction, we actually don't have a model that can really scale at similar levels yet. And I really believe like scalability is the fundamental problem we need to address to make 3D techniques actually accessible and useful for all the users. And in today's talk, I will cover some of our recent works on improving the scalability of 3D reconstruction and rendering models from multiple perspectives. And first, let's talk about what a scalable 3D model should be able to achieve. And in my mind, a truly scalable model must accomplish at least three things. The first is inferences at scale, meaning the model must compute and generate output at extremely high speeds and provide real-time responses to users. And in fact, improving inference scalability has been actively studied across various 3D methods. For example, when NeRF was first introduced, it delivered remarkable visual quality, but it required several days to reconstruct even a single scene, and its rendering speed is also slow, taking around 30 seconds per frame. And over the recent years, we've seen significant improvements on the inference speed side with new representations and new techniques like planoxels, TensorF, NGP, and also more recently, we have the 3D Gaussian splatting. And now, with all these advancements, we can reconstruct a scene in about 10 minutes and achieve real-time rendering with 3D GS-based methods. This is, of course, a huge improvement. However, if we compare with other fields, we're actually still quite slow. For example, for like large language models like ChatGPT, which is already used by millions of users worldwide every day, it can actually generate responses almost instantly in real time. And these large models are actually running at a super large scale, which has never been achieved by 3D models. And at Adobe, we were trying to address this scalability challenge by building various 3D large reconstruction models. For example, the first large reconstruction model proposed by my former colleagues at ICR 2024 was able to achieve high-quality nerve and mesh reconstruction in seconds from a single input image and produce high-quality null view synthesis results as shown here. And since then, we have been working on trying to keep advancing the scalability of 3D large models. And recently at ACCV 2024, our work GSLRM can achieve 3D Gaussian splatting reconstruction in less than half a second and achieve these high-quality real-time rendering results as shown here. And the key we are able to achieve this is to enable learning at scale. And this is the second key aspect I believe a scalable 3D model has to achieve. And of course, right now, in most cases, person optimization-based neural rendering techniques still achieve the best visual quality. But it often requires dense image captures and relatively long inference time, as we mentioned. So we actually need to build feed-forward models that can do learning at scale across large data sets so that we can leverage strong data priors to achieve fast and high-quality reconstruction with any number of input images. And the third aspect I want to mention about a scalable 3D model is the modeling scalability. And specifically, I mean the size and the levels of details in the scene we can model with the system. And I think this is also an aspect that is very relevant to this workshop. And I really appreciate and excited to see the efforts that has been made here on building large-scale 3D scene data captures. And in fact, on the other hand, we can see that there has been a lot of methods for 3D Gen AI techniques, which are like proposed in recent years. But we can also see that most of those methods actually still focus on object level 3D generation and reconstruction, including the original LRM. So in our recent GSLRM, we actually improved the modeling scalability and enable our model to achieve high quality scene level reconstruction from only 2 input images and enable high quality null synthesis results as shown here. And again, the reconstruction only happened in less than half a second. And in GSLRM, we're only able to process 2 to 4 input images. So the scale of the scene we can model is still relatively limited. So recently, we further addressed this problem in another recent work called long LRM, where we are able to enable wide coverage scene level reconstruction from as many as 32 high resolution images in a single feed-forward pass. And this further significantly boosts the modeling scalability. And for the first time, we might see the potential to fully replace person optimization methods with scalable feed-forward models on long sequence inputs. And later in my talk, I will cover the details of these works. So in general, I highlighted 3 key aspects a scalable 3D reconstruction model needs to feature. So we basically need to achieve inference at scale, learning at scale, and modeling at scale. And as mentioned, these are also the key aspects our recent works are trying to improve. And on the other hand, enabling these scalabilities also require us to carefully design and improve our model from multiple perspectives. This often includes improving the 3D representation, the model architecture, and the data. And in a sense, all our recent works I'm presenting today are trying to improve these individual components in the system to boost the model scalability. And one of the key philosophy that is shared across all of our work is to consider 3D reconstruction as one sequence-to-sequence token translation task, just like how other large AI models are solving their problems in their fields. And this idea is in fact inherited from the first LRM work, which was designed for single image 3D reconstruction. And the first LRM leveraged a DIT, a Dino-VIT model to tokenize an input image into a sequence of tokens. And it also represents the scene as a triplane nerve and tokenize the triplane features with learnable token embeddings. So essentially, LRM achieves 3D reconstruction by adopting a scalable transformer model to translate the input image token sequence into the output triplane nerve token sequence, which is doing an image to nerve translation task just like how a GPT model can translate one language to another. And after the initial LLM work, we have developed many more large reconstruction models to improve the model's scalability. For example, in the work Incident 3D, which is another ICR 2024 paper, we extend LLM from handling only a single image to multi-view reconstruction from 4 input images. And combining it with multi-view image diffusion models, we further enable fast text-to-3D generation. And in another ICR paper called PFLRM, we studied object-level reconstruction from unposed images using a large single-stream transformer model. And in another recent work called Mesh LLM, we focus on the learning and inference scalability by designing a faster LLM model that can directly output high-quality mesh assets in less than 1 second. And as we can see here, all our previous work still focus on object-level 3D reconstruction. And one of the key reasons there is also like in all this work, we leverage the triplane nerve representation, which is actually bounded in 3D. So in our recent work, GSLRM, we successfully switched our representation in LRM to 3D Gaussian splatting, which is a more scalable representation and enables scene-level reconstruction. For example, given these 2 input images of a real scene as shown here, our GSLRM can instantly reconstruct the 3D Gaussian splatting representation in about 0.2 seconds and achieve real-time rendering with high visual quality as shown here. And compared to previous object-level triplane LRMs, GSLRM actually improves the scene modeling scalability as well as the learning scalability and inference scalability. And again, we achieve this by solving a sequence-to-sequence translation task. Where the image is not showing. Let me see. Never mind. I don't know why there's supposed to be some input images, but anyway, imagine I'm showing image here, input images here. So essentially in GSLRM, we consider input images and there are no camera poses as input. And in GSLRM, we parameterize the camera poses as per pixel Planck array coordinates that are concatenated with the input. And we tokenize these input images with a simple petrification layer and a simple linear layer. And we pass these tokens into a sequence of purely self-attention-based transformer blocks to regress the final 3D GS parameters for each 3D pixels, which are then combined as the final 3D GS output of the scene. And here we can see that our GSLRM model actually has a very simple architecture, which is almost just a self-attention-based transformer. And if we compare this with the details in the original large reconstruction model architecture, as shown here, we can see that a lot of things have been improved or actually simplified. In the original LLM, it still handles a single input. It has a heavy DynoVIT-based image tokenizer. It still uses cross-attention, and it uses add-in-based camera conditioning, and it also uses like triplane nerve representation, as mentioned. And in GSLRM, these are all different now. But these changes are actually not made by a single work. Specifically, like the extension from single view to multi-view was made in the Instance 3D. And the removal of the Dyno tokenizer was also studied in Mesh LRM, our first work. And in Mesh LRM and PFLRM, we have also studied using a single stream transformer without the cross-attention layers in the original model. And in another work called DMV3D, we studied replacing the complex camera conditioning into the simple Planck array-based parameter coordinates. And finally, in GSLRM, we combine all these changes and further replace the triplane representation with the 3D GS representation, which leads to this simple but highly scalable large reconstruction models. And in general, we don't think simplicity is a bad thing. In fact, in many cases, we feel that simpler designs often lead to more scalable models and bringing us better visual quality and efficiency. So for example, here, if we compare our GS-LRM to the previous nerve-based LRM model in Incident 3D, we can clearly see that GS-LRM can offer better visual quality with many more high-frequency details. And this is, of course, because of the better learning scalability in GS-LRM. And here, as shown in the table, actually GS-LRM has like even fewer model parameters and uses much less compute resource compared to the previous nerve-based LRM. And this showcases that our GS-LRM can scale more efficiently than previous models. And importantly, because the 3D GS representation can easily model unbounded scenes, GS-LRM can achieve scene-level reconstruction as shown here, enabling better scene modeling scalabilities. And for the scene-level reconstruction, our GS-LRM is trained on the real S10K dataset, containing more than 60,000 training sequences with both indoor and outdoor scenes. And accordingly, our GS-LRM can also work on both the indoor and outdoor scenes and produce high-quality novel view synthesis results. And if we compare with previous and concurrent works on the same training and testing set, we can see that our model can achieve significantly better results, outperforming the previous method by a large margin of more than 1.5 dB in PSNR. So overall, in GS-LRM, we switched the large reconstruction model representation from NERF to 3D GS, and we also introduced a simpler but more scalable network architecture, and we also added the real S10K scene dataset in the training set. So all these features combined allow us to successfully boost the scalabilities of 3D large reconstruction models from all these perspectives. However, in GS-LRM, as mentioned, our model can only process 2 to 4 input images, which can only model a limited size of scene. But when we want to capture a full 3D scene with a lot of content like this, one would at least need several tens of images as input and move around the scene and do captures. But so far, no feed-forward models can actually handle a big number of inputs like this because the scale of the input is too large. And usually we would need to use the neural rendering techniques like the original 3D GS to reconstruct the scene with about 10 minutes of percent optimization. So to address this, we recently proposed the work Long LRM. And this work was driven by our former intern Zuwen Chen from Oregon State University. So in Long LRM, our model can directly reconstruct this large 3D scene in a feed-forward path in only 1.3 seconds from all these input images. And here, I'm showing an overview of the final 3D GS reconstruction from all the previous images. And then with this, we can render the scene from a wide range of novel viewpoints with high visual quality, as shown here and with this video. And in general, Long LRM can support up to 32 high-resolution input images, which can already model a wide scene coverage as shown here. And with the same input, our model can in fact achieve comparable and sometimes even better rendering quality than the percent optimization-based 3D GS techniques as shown in these figures. And this is for the first time we see the potential to actually replace optimization-based methods with feed-forward models when we have a long input sequence of images. And in fact, processing so many input images is a highly challenging task, especially when we are trying to use sequence-to-sequence processing models. And to clarify this, I'm showing the context lens comparison between our GS-LRM and Long LRM models. Basically, Long LRM considers input images at a much higher input resolution, and we consider many more input views. This leads to a long sequence input of about 250,000 tokens, which is more than 10 times tokens used by GS-LRM. And this is also like extremely long input sequence in general. Note that the context length of a modern large language model like Llama 3 is only about 128,000, which is even shorter than ours. But remember, like models like Llama 3 is trained with more than 10,000 GPUs, and we instead, as shown here, are still trying to solve this problem with using like only 64 GPUs. So this is actually quite challenging. And the key to make this happen is to leverage the recent Mamba model, which is a state space model that is designed to handle long context reasoning more efficiently. And in a sense, unlike the attention-based transformer that is known to scale quadratically in terms of the length of the token sequence, Mamba model can scale linearly and leading to a significantly lower time and memory complexity, and allowing us to handle much longer input sequences. And in our long LLM, we utilize a hybrid architecture that combines both the Mamba 2 blocks and attention-based transformer blocks. This allows us to achieve a decent balance between training efficiency and reconstruction quality when processing long sequence inputs. Now here's the full framework of our long LLM. We actually tokenize the input and images in the same way as GSLM, and then we send the tokens to our hybrid model to regress per pixel Gaussians for the final GS reconstruction, also similar to the GSLM. And in order to further cut the compute and memory costs, we also apply additional token merging and Gaussian pruning techniques, which further improve the scalability of the model to support even longer input sequences. And in our paper, we present a comprehensive ablation study on all of these components, and please check the paper for more details. So basically with long LLM, we now can process these 32 high-res images, do the reconstruction in only like 1.3 seconds, and achieve high-quality null view synthesis rendering as shown here from a wide range of scene space at a lot of viewpoints. And for long LLM, we use the recent DL3D-V dataset to train our model, which contains more wide coverage scene captures than other datasets. And this allows us to achieve high-quality wide coverage 3D GS reconstruction on various scenes, including both indoor and outdoor scenes, as shown here. So we can say our model can model the shading effects, like the specularities and the transparencies in these scenes. And here I'm showing like some outdoor scene examples. Like even on these 360 camera trajectories, our model can work well and produce recent high quality results. So in long LLM, by leveraging a hybrid network architecture and a new dataset, we are able to further boost the scene modeling scalability to enable much wider scene reconstruction than previous feed-forward models. But one thing to note is that in long LLM, we still use per pixel 3D Gaussian as the model prediction and representation, which in fact can lead to challenges when further scaling up to more inputs. Because the more input we have, the more Gaussians we need to model and render. So again, the choice of the 3D representation kind of becomes the bottleneck that makes it uneasy to further scale up. And in a sense, if we review what we are actually doing in all these different large reconstruction models, we basically first select some 3D representations and then design a model accordingly to regress the 3D representation we choose. And we reconstruct this in a sequence-to-sequence translation manner. However, this actually imposes strong 3D inductive bias in the model, which might actually limit the model to learn and scale better. And from the experience in other AI fields like NLP and image generation, we know that in most cases, fewer inductive biases often lead to better scalability and quality. So an interesting question to ask is, do we actually need 3D inductive bias in scene modeling, especially when we only care about view synthesis and rendering quality? So we studied this problem in a very recent work called Large View Synthesis Model that is just accepted by ICRI 2025 as an oral. And this project was driven by our former intern Haiyan Jin from Cornell University. In this work, we try to keep reducing the 3D inductive bias we leverage in previous large reconstruction models and do novel synthesis. And we study the problem with the setting with 2 input images as we did in the GSRM. And in the end, the conclusion we have is, interestingly, is that the fewer 3D inductive bias we have, the better quality we can achieve. For example, here are some novel view synthesis results from our large view synthesis model, taking the sparse 2 input images on the bottom as input. And we can see the results are of very high visual quality. It produces many sharp high-frequency details, and it recovers complex shading effects, including those like here, the reflections, the specularities, and it recovers all these effects very realistically. But all these results shown here are actually generated by a model with very minimal 3D inductive bias without any predefined 3D representations. And in large view synthesis model, we in fact remove the 3D inductive biases in LRM in 2 steps to better understand the problem. And this corresponds to 2 different network architectures. So first, we introduce an encoder-decoder large view synthesis architecture, where we replace the predefined 3D representations with a purely learned scene representation. And specifically, we still tokenize the images with like very simply using petrification and a single linear layer, as what we did in the GSRM and LongRM. And on the other hand, we represent a scene by a fixed number of 1D learnable tokens without any 3D inductive bias at the representation level. And we again consider the scene reconstruction problem as a sequence-to-sequence translation task, and we apply an encoder transformer network to map the input image tokens into the learned scene representation tokens, as shown here. And then to achieve novel view synthesis, we directly take the blocker ray coordinates of the target view, tokenize it into target view tokens, and then send them along with the learned scene representation tokens from the encoder to the decoder transformer, which can regress the final target view images as shown here. So in a sense, in this encoder-decoder large view synthesis model, the encoder network functions as a scene reconstruction model that can transform the input images into the 1D latent tokens, which is a fully learned scene representation. And the decoder network is actually like a rendering model that can render images at any novel viewpoints from the learned scene representation. And in this process, we have fully removed the representation level 3D inductive bias like NERV or 3D.js we have used in previous larger reconstruction models. But this encoder-decoder network also still has a major bias that an intermediate scene representation is still needed, although it's fully learned. So we take a step further by proposing a decoder-only large view synthesis model, as shown here, which can directly regress the final novel view images from multi-view input image tokens and the target view blocker ray tokens without even using any intermediate scene representations. And this leads to a large view synthesis model with very minimal 3D inductive bias. And in both encoder-decoder model and the decoder-only model, we adopt fully self-attention-based transformer blocks like what we did in our GSRM and MESH-RM model. But now we don't have any 3D representations at all, so these are actually even simpler network architectures. And again, we don't feel simplicity is a bad thing. We actually find that the simpler the network is, the better scalability we can achieve, and which can further bring us better visual quality and efficiency. And here I'm showing the quantitative results compared with all previous works on the real S10K dataset. We can see that without any predefined 3D representation, our encoder-decoder LVSM can already achieve high rendering quality that is even slightly better than the previous state-of-the-art model, which is in fact our GSRM model. And by further removing the representation, our decoder-only LVSM model can achieve even significantly better rendering quality with a notable improvement of more than 1.5 dB in PSNR over our GSLRM model and our encoder-decoder architecture. And here I'm showing some visual comparisons. We can see that our GSLRM model can clearly outperform other baseline methods like pixel splat, MV splat, which are also based on Gaussian splatting representations. But our scalable solution achieves better visual quality. And our decoder-only LVSM model achieves the best of visual quality with even much fewer artifacts. And here we can see that although we don't have any explicit 3D representation, our novel view synthesis results are actually very consistent across viewpoints, and it well represents the complex shading effects and geometry details in the scenes, and is even more consistent than many of the methods that actually use 3D representation. Now here I'm only mainly showing some scene-level rendering results, but in fact, our LVSM model can also work well on objects. And here I'm showing some object-level results quickly, and the model can produce very consistent rendering across these large viewing changes around 360. And here I'm showing more results from our large view synthesis model. Again, our model works well on both indoor and outdoor scenes. For example, it can well capture the complex glass reflections on the left scene, and it also captures the zooming in details on the right scene very well. And another interesting point to note is that we find our large view synthesis model actually has very strong zero-shot generalization ability. For example, we find that our model, which is always trained with multi-view input images, can be directly applied to do single-view novel view synthesis with reasonable quality as shown here. It can model the parallax effects reasonably well, and it can model the shading changes across views reasonably well. And of course, we are seeing more artifacts than the multi-view setting, but this is as expected because the model is never trained on this single-view input setting, but it still performs reasonably well. And this is actually very interesting since it kind of suggests that the large view synthesis model without any 3D representations is actually trying to understand the actual 3D in the learning process from the image data instead of simply copying pixels. So in general, in LVSM, we focus on enhancing the learning scalability. We completely remove the use of any 3D representation, which allows us to adopt a transformer-only architecture with minimal 3D inductive bias. And this leads to a highly scalable 3D model that can achieve state-of-the-art rendering quality. And in this work, the inference scalability is not our main focus, but actually the model can also render at very fast at real time, which is faster than NeRF-based models, although slower than the GS-based models. And here we are also not focusing on modeling long sequence input as what we did in long LRM, but potentially we can of course combine a large view synthesis model with the long LRM to achieve long sequence reconstruction. And importantly, now we don't have any 3D structures and rendering components in the system, so we basically only have a transformer model that is almost. Sorry, I'm hearing some echoing.
Okay. No, go ahead. Let me mute the guest.
Okay.
Go ahead. Sorry.
Yeah, so basically we have a transformer model that is almost identical to the foundation AI models in other fields like large language models and diffusion transformers. And this means that we can now easily apply all the scaling up techniques that have been already adopted in other fields to further boost the scalability of the model, which this means like a lot of potentials. For example, we can do things like sequence parallel, we can do pipeline parallel, tensor parallel, and we can do MOE. We can even do the new high-speed inference techniques like the latent attention techniques proposed by DeepSeek. So we can do a lot of things because now we only have a scalable transformer architecture and we have no other complex inductive bias. But unfortunately, we have a lot of potential to further scale up the model. There is one thing that might just stop us from doing anything, which is that we don't really have enough 3D data especially scene level data, to train our model. So we are trying to address this challenge in another recent work called Megascenes that is just accepted by CVPR 2025. And this work was driven by our former intern Hanwen Jiang from UT Austin, and the project was led by my former colleague Hao Tan at Adobe. And in this work, we aim to further scale up 3D reconstruction with synthesized data. And the key idea is to leverage procedurally synthesized 3D scenes and computer graphics rendering techniques to create infinite amount of data like this for training 3D models. And you might see that these things might not look very similar to real 3D scenes, but we show that these things are actually still useful for training scene level 3D large models. And in some sense, like which one thing I haven't mentioned was like the real scene data we have nowadays are still quite limited. Like the DL3D data we use in our previous long ARM work, it only has like 10,000 scenes. But with this procedural framework, it means we can synthesize as many scenes as we want, and we can easily scale this up to 1 million. And procedural data generation is in fact a problem that I have been interested in for years. And in fact, the first work I worked on this direction was done when I was still a PhD at UC San Diego in 2018. And at that time, I built a fully synthesized 3D object dataset by creating 3D geometry with manually designed procedurally generated random shapes and combining these shapes with random high-field displacements and textures. And this leads to actually highly diverse 3D assets, as shown here. Although they look quite different from real objects at a global scale, they actually share a lot of similarities to real objects at local scales. And they, at many times, they can be even more complex than real data, which is enough for us to train some strong 3D models. And at that time, we have studied using such synthesized data to train neural networks and do various interesting graphics and vision problems, like relighting, view synthesis, and inverse rendering, as shown here. However, at that time, we don't really have a scalable model architecture, and the experiment scale we can conduct was also very limited and preliminary. But now we have the strong transformer model, and we have the 3D large models we have already built. We can leverage these data and revisit. So in the NeurIPS 2024 paper, we revisit the procedural data generation pipeline and further largely extend its scalability and diversity. And with this, we built an object-level synthesized dataset called ZeroVerse, which we use to train an object-level large reconstruction model, which we call LRM0, without using any artist level, without using any 3D assets that are created by artists. So all this data are synthesized by our computer algorithms. And we found that LRM0 can actually produce very high quality view synthesis results that look, sorry, the video are not playing. Sorry, but actually, okay. These videos also look quite high quality, and they look visually comparable to the GSLM model that are trained on the Observerse data with artist-designed 3D assets. And this kind of suggests that a promising direction to solve the 3D data problem is to scale the data with the procedural assets. So in Megascenes, we further extend the synthesized procedural data to build diverse scene-level assets, scene-level dataset like this, which allows us to improve our scene reconstruction and rendering quality. And in Megascenes, the data generation process is also much more complex than Object 1, since we now have more dimensions to consider. And the full pipeline includes multiple stages. We start from floor plan generation to procedurally create some 3D bounding box in the scene for us to place individual objects. And then we synthesize each object using the same technique we did in the LRM0 and ZeroVerse, and we create those individual assets and we compose them in the scene according to the floor plan. And then we further create lighting in the scene, and we also procedurally create a camera trajectory around the scene for the final image rendering. And the whole process is done in a fully automatic and procedural way, allowing us to easily scale up our data to create as many as scenes we want with diverse results. And note that in such synthesized data, we actually don't have any meaningful semantics information, but our data can provide accurate 3D correspondence and ground truth 3D labels like depth and objects instance. And these are something like real data are actually can actually hard to provide. And we also found that this ground truth 3D information is in fact quite useful when we are training our large 3D reconstruction models and rendering models. So we evaluate our megasynth data by combining it with the small amount of real data to train our 3D large reconstruction model. And as shown here, the real data percentage is only about 1%. And this is actually the full data set we can access from the DL3DV dataset. And we create like 700K scenes with megasynth very easily because everything is procedural. And we've found that adding our synthesized data in the training process can consistently improve the final rendering quality on both JSLRM and long LLM compared to training only on the small DL3DV dataset. And here I'm showing some visual comparisons. We can clearly see that our megasynth data can improve the reconstruction quality and lead to more accurate 3D structure predictions with more details. And interestingly, we also found that even using our synthesized data alone can also lead to reasonable rendering quality. Of course, we still see some gap here, but the gaps are small. And like it's quite surprising, like with only synthesized data, the model still works. And this kind of suggests that 3D reconstruction is quite a low-level task that doesn't require that much semantic information. So in the future, it will be very interesting to further investigate this direction and design better procedural rules to further scale 3D scene level data in a more effective way. All right, so I just want to quickly conclude my talk. So today I present our recent work on scaling of 3D large models, including our 3D, our GSLRM and long LLM model that are designed to achieve scene level 3D GS reconstruction in a feed-forward manner. And I also present our large view synthesis model work, which aims to remove the 3D inductive bias in 3D modeling for better learning scalability. And our megasynth studied the problem of scaling up 3D large models from the data perspective, which is also very important. So in general, the general goal of all our recent work is trying to build a scalable 3D model that can achieve inference at scale, learning at scale, and modeling at scale. Thank you, and I'm happy to take any questions.